Hello, hello. How are we all? Awesome. Just tuning into the chat. I'll get a poll going and I'll answer your questions. Okay. Right, so we have got rates. We have got organic chem. We have got chem of the atmosphere. We have got chemical analysis. Oh, it's good. I can only do 4 options, which is good because I avoid doing using resources, which is boring. Right, so let me write something on here so people don't think I'm just mucking around. Lovely stuff. Right. Okay. Okay. So I really like your question. By the way, hi. I don't know if you have an actual name. In terms of triple, yes, it's like a one line in the specification that you about how you can make some of the stuff for NPK fertilizers. Are you aware of how to actually look at the specification? By the way, if you ever have questions like that in the future, not that you're going to have many more questions of it. What I'll do is I'll whack that in the chat. Look, so if you ever go on the spec, right? Is this triple? It'll be a bit of everything. We can do using resources. I think using resources is a little bit airy-fairy, though, if I'm honest with you. Like, as in, as long as we can work longer answer questions, I'm sure we'll be all right. So I think, like, so if you ever look at the website, right, in the subject content, you can click on it, and it's literally everything you need to know. I know it's like aimed at teachers, but there's no reason for you to access it. So you'd asked about phosphate being treated with acid to produce phosphates for NPK. Yeah, that's just one line in there. It says phosphate rock is treated with nitric acid or sulfuric acid to produce soluble salts that can be used as fertilizers. It's one of those like one-liners, I would say, like that a spec can have, in the same way that you can have like Chadwick discovering a neutron, for instance. Right, so we've also got someone who asked about alkanes and alkenes. I'll let the poll go on for a little bit longer. We'll do that. Obviously, if you have... Perfect. Awesome. Yeah. So, like, I think sometimes teachers are really hesitant to tell you, like, the exam spec, but it's literally a list of everything you need to know, so why on earth would they? As I said, any other questions, whack them in there. I will end the, like, poll in a minute or so. I know we've got a question already about alkanes and alkenes. I know you've also asked about doing some more using resources. Absolutely, you can do that. But any specific questions, obviously, whack in. Alkanes and alkenes will definitely do as we do organic chemistry. So do not worry about that. That's my personal favourite. I'm a chemist, really. That's I do all of them. But chemistry is my favourite. And organic chemistry is fun. It's like puzzles, isn't it? Okay. Let's end the poll. Okay. So rates followed by organic chem. I know you've kind of got a vote in the background. In the background for using resources. We can do that as well, right? Let's look at rates. Okay. Fundamentally, rates, I suppose, comes in 2 halves, right? Rates comes in 2 halves. Rates comes in our ability to use maths, and rates also comes in the idea of collision theory, mainly. Okay, so when we're looking at rates of reaction, Okay, I always like to link it to collision theory. And then you've got the practical and like kind of experimental side of it. So collision theory fundamentally says this. Okay, for chemicals to react, the particles must collide. And not only that, they've got to collide with enough energy. And I think in my head liken that to putting a lid on a pen. If I want to put a lid on a pen, I know it sounds obvious, the lid has got to touch the pen. But that's not enough to put the lid on. Oh, great. Love that. Now's the time. That's not enough for it to be deemed the lid on the pen, right? I need to make sure it has sufficient energy that it clicks on and it is deemed reacted. Okay. So if I can affect one of these two things or both of them at the same time, I get a faster rate of reaction. And that means that there are 4 ways that I can change. 4/5. It's 5, but it's 4 really ways that I can change the rate of reaction. So the first way is Sean Paul's favourite way, which is the right temperature for shelter you from the storm. Okay, and if I think about increasing the temperature of something, just the camera. Woo, parkour. I don't like that. There we go. Right. So if I think about temperature does 2 things fundamentally. It increases the kinetic energy of the particles, right? So that means we have increased kinetic energy. So that means that they are moving faster while you're coming fast, and that means that they have more. The collisions will be more energetic. So if we're going through a full explanation, right, and these are usually like 3 markers, something like that. Okay, what's the effect of temperature on rate of reaction? Okay, higher temperature means faster rate. Why is that? Because the particles move faster with more energy. What does that mean? If I made you all run around in a room, you're going to have more collisions. That means there's more collisions. And those collisions also have enough energy. And if there is more collisions with enough energy, then we say there is more successful collisions. This idea of there is a higher rate of successful collisions is what explains the whole thing. Okay. Right, so that's temperature. Now I can do concentration, which is basically pressure as well, right? So concentration is a liquid and pressure is a gas. So if I have a higher concentration, that is like I've got more particles in the same space. Okay, so more particles in the same space. Or volume, that'd be better, wouldn't it? If I have more particles in the same volume, that means there's going to be more collisions, because if I put more of you in a room, you're going to bump into each other more. If I have more collisions, I have more successful collisions, and therefore faster rate. Can you see this formulaic nature of this, right? Like it's this happens, then this happens, and this happens, and this happens. Right, next one is surface area. Okay, so the kind of insight here is that solids react at the surface, right? Okay, how are you going to react with a solid? The particle's got a bump into it from the outside. So if I took this and all I did was cut it in half, well, look how many more places I have got to hit, right? So that is what we call. I know we talk about increasing surface area, but really what we're doing is we're increasing surface area to volume ratio, similar to like when you did conservation of heat and biology, right? So if I'm increasing the surface area to volume ratio, that means I can have more collisions at the surface. If I have more collisions at the surface, that means I have more successful collisions. And if I have a higher rate of successful collisions, that was a typo with a hand. How do you have a typo with a hand? Who knows? That means I have a faster rate. Okay, now we've done temperature, we've done concentration and pressure, we've done surface area. That leaves one more, which hopefully is brewing in the back of your head. It's like when you see a plot twist coming. Hello, Tiggy, how are you? Oh, the cat is shy. I cannot pay the cat's tax. Look at that. Who has that colour as a felt tip? It's the colour of vomit. Right, there is one thing left. Okay, which is the catalyst. Now, catalysts. Oh, look at that. The cat walking past for a catalyst. That is timing. Right, catalysts. So if we think back to paper one, we did reaction profiles, right? Where you had the energy level of your reactants and then the energy level of your products. In this case, because it has dropped, this would be an exothermic reaction, incidentally. And we always drew the hump, right? And that hump represents this, which is our activation energy. And that is the amount of energy needed for reaction to actually take place in the first place. Okay, so that's our minimum energy required to react. So if I go back to the idea of a reaction being I'm going to put a lid on a pen, right? The activation energy would be the amount of energy it takes for me to click that lid on. Okay. Now, a catalyst, we know hopefully from outside that makes reactions faster. It doesn't get used up. And it's often credited as providing what we call an alternate pathway. So in this situation, right, really, my hands have been a catalyst the entire time. Because in true collision theory, I would literally just throw these at each other and maybe, like one of those trick shots, where people throw like CDs in like a games console from afar, or they like put a hanger on a rail, right? That can happen, right? I could, from the other side of the room, launch that lid and it hit perfectly, but that's really difficult, right? My hands have guided that in, and it means that I need less energy to click the lid on because it's kind of hitting perfect each time. I've also, in class as well, described it as like if you ever go to a theme park, right? The activation energy is saying like you must be this tall to ride, okay? And if you're shorter than that, you don't get on. Well, what a catalyst does, and let's do this in purple, is it provides an alternate pathway, so it lowers that activation energy. So instead of having to go that big hump here, it kind of still has a hump, still got to have activation energy, but it's lower, right? So the catalyst lowers the activation energy. So if I go back to my concept of collision theory being that the particles must collide and they must collide with enough energy, if I've lowered that activation energy, that means more of those collisions which are naturally happening are going to have enough energy. Okay, that means more collisions will have sufficient energy. And if more of those collisions have sufficient energy, that means we have more successful collisions. And if I have more successful collisions, okay, then I have a faster rate. So that's kind of the theory with rates of reaction. And that's the idea of collision theory. I'll do the experimental side, and then I think I'll talk about reversible reactions because that does overlap slightly with using resources. So I might use that as a way in to looking at the Haber process, all right? So you have, when we were measuring rates, right? Rates fundamentally can be measured in two ways. You're either looking at how fast a product appears, or you're looking at how quickly a reactant disappears. And all the required practicals revolve around that. So let's give an example of a product appearing. The classic one is when you did, and hopefully it rings a bell, where you have a conical flask and underneath there, you put a cross on a piece of paper, you had the liquid in there and it started to go cloudy, and then you hit the stopwatch when it had blocked the cross. So you are essentially measuring how quickly that product has appeared, blocked it out, and that's how you can measure it, and you can plot that on a graph. Measuring the reactant disappears. Well, how can I do that? One of the classic ways is you do one on like a scale. I've got 2 into draw in this for some reason. There's my number, right? And if I did my conical flask on here like this, and let's say I added acid and then I put like carbonate rocks in there, right? So what would happen is those carbonate rocks would fizz like this, and there won't be bubbles anymore, would it? The gas would escape, so you'd watch that mass go down, right, on the scale. And that's the fundamental idea of the experiments, right? Weirdly, I don't want to go into in depth about specific examples, but more the concept, right? I am either seeing how quickly products are appearing or how quickly reactants are disappearing. All right. Just another thing, just while we're on the subject of variables, remember our types of variable. I always like to talk about dairy milk ice cream. So the dependent variable is what you measure, and the independent variable is what you change. And the question will usually set up by saying a student, I mean, if I've got one to hand here, it won't take me long to find one. He says, a little bit of that. Come on. Yeah, look. Right, so this one, it says, look, a student investigated the rate of reaction between zinc and sulfuric acid. The equation is here, okay, and then they measured the appearance of the gas. And usually it would then say, right, if I look at the next page, look, a different student investigated how the concentration affected the rate. Now, because they've mentioned concentration, that means that is our independent variable. That is the thing that they have decided to change. Yeah, I can go through sewage water treatment at some point. Don't you worry about that. Okay, so everything else apart from the independent would be a control variable. And often those control variables will be those rates bits that we went through earlier, right? So if I'm looking at concentration, I want to make sure the temperature is the same, or the surface area is the same, or that, like, if I'm using a catalyst, I just use that the same. So the control variables basically become your other ones from the rate. That's the main prospect of that. The other thing also is when you plot it on a graph, I'm just going to draw a random line that say the reaction looks like this. The two things to remember is when you get this flat line like this, okay, that means the reaction is over. Right? It might mean that all the reactants are used up. If it says, right, what is the initial rate of reaction? What practical do you have to learn? So I'm trying to be quite general, but the two ones mainly are when you have a reaction like this and gas is produced, and you either collect the gas in a measuring cylinder or a gas syringe. So one of them, it bubbles up into there. Okay, or it's the thiosulfate practical where it goes cloudy. Both of those are fundamentally like the same thing, which is why I kind of haven't gone through a step-by-step guide of each one. As I said, like it's weird without the equipment in front of me. I think I'm going to do a bad job at that. So I've always recommended Malmesbury Education. If you just literally type in rates required practical into YouTube, you can watch them do the practical, and I think that's often a little bit better. So here I've got the rate graph. No, because electrolysis is not on this paper. You're fine. Or are you talking about electrolysis for the extraction of metals? In which case, it's not really as much as a theory. So if I'm going through the initial rate of reaction, I have to draw a tangent. If I want to look at it, draw a tangent to the curve, and then I look at the gradient of that. Okay. I did say to kind of round off rates, I would, I'm going to now look at reversible. So when you say Le Chatelier, that's what this is about. That's what I was saying about electrolysis doesn't really come up. The only thing you need to know about electrolysis is it's a way that you can extract metals. Right. So I think that the reversible reaction symbol is one of the cooler symbols because, it's like an arrow going both ways, which makes sense. Okay, so a reversible reaction is one in which the reaction can go both ways. I think we're happy. I'd like to think we're happy with that. Yeah, so that's what I was saying about that practical. So there's kind of two. There's that one, and then there's the gas appearing one. Those are your main two. This leads to something called equilibrium eventually. Now, equilibrium. So this just simply means you've got a reversible reaction. Okay, and what equilibrium means is that the rate of the forward reaction is equal to the rate of the backward reaction. Okay, now this is quite hard to get our head around, especially when we start talking about Le Chatelier's principle. Equilibrium as a concept is on foundation. Le Chatelier, it's really, they only reserve that for higher. I think it might technically, a small chunk of it be on foundation, but if they ask that, that's crazy time. All right, I don't think so. I think it's just the concept of reversible reactions and the concept of equilibrium on a foundation. Right. How am I going to explain Le Chatelier's principle? Okay. So, many of you, I'm sure, have younger siblings who are annoying, right? Like a younger brother, younger sister. And if I told that younger brother or younger sister, don't do something, we're kind of, in a roundabout way, getting to NPK fertilizers. I think people are kind of getting a little bit caught up on NPK fertilizers. It's not as difficult, I think, as people think. We'll come to that when we do organic. I'm noting them down. I know I've got to do alkanes, alkenes. We've had a question about NPK. I'm now doing Le Chatelier's principle. We're going to talk about esters. Okay, we've had electrolysis, but I'm going to put that in quotation marks because you don't need to know it in any way of the detail of paper one. It just basically means you extract using it. Okay, so I'll put that there. What should we be doing to get grade 9? Do a little bit of revision, get in that habit, enjoy your subject. Probably, I'll be honest with you, prioritize sleep instead of watching a live stream at 8 o'clock at night. If I'm honest, enjoy yourself. Okay, so Le Chatelier's principle. All right. I've mentioned the idea that you have younger brothers and sisters, maybe some of you. What Le Chatelier's principle formally says, okay, is any change in conditions causes the equilibrium to move to minimize the change. Now, what does that mean to me? If I tell my younger brother or sister, get down from the table, they're going to stand up on the table. If I tell my younger brother or sister, stop poking the balloon, they're going to start poking the balloon. If I tell a chemical reaction that I'm going to increase the temperature, it's going to do everything it wants to reduce the temperature. Okay, so the classic example we always talk about is the Haber process ammonia reaction. So in that, we have 3 H2O plus N2, reversible reaction to NH3. And all of these are gases. Okay, this reaction is actually an endothermic in the forward direction, which means it's an exothermic in the backwards direction. Now, I said that equilibrium means the rate of the forward reaction is the same as the rate of the backwards reaction. Now, if you ever go to a shopping centre, and here's the escalator, right? If the escalator is moving down and I run up the escalator, I actually wanted to film this in secretly, but I never had the courage, I'll be honest with you. If I run up the escalator, from the outside, it looks like that person is not moving, right? If they run the same pace as the escalator, they'll do that. Now, this is why some people find it really hard to get the idea of the position of equilibrium can change, right? Because if I run a little bit faster, I might go a little bit higher up the escalator before I reach that kind of balance point again. So when it says about shifting the place of the equilibrium, I could balance out the escalator up here, but still not make it to the end. And same here, right? I could slow down a little bit, in which case I'd drop further down. So it's the same thing with a chemical reaction. Oh, thank you. Oh, that's nice, isn't it? So I could shift in those directions. So when we talk about equilibrium, sure, can I do some kind of weird super light, like on some kind of like, oh, don't know if I can. Shocking. Well, I can do a heart react, can I? Oh, lovely. Look at that. Stream of knowledge. Right. So if I go back to our reaction here, which is the Haber process, right? If I say, right, if I increase the pressure, right? The Le Chatelier's principle says that any change will cause the equilibrium to move to minimize the change. So if I increase the pressure, the reaction becomes like our annoying younger brother or sister. Well, if you're increasing the pressure, I don't want that. I want to decrease the pressure. Okay. If I look here, on this side, I've got 4 lots of gas, 3 hydrogen and 1 nitrogen. And over here, I've got 2 lots of gas. Okay, so over here, I've got less gas, and over here, I've got more gas. So if I increase the pressure, what happens is the reaction says, I want to minimize this and try and decrease. So what happens is our equilibrium shifts to the right. So we shift to the right. So therefore, we equilibrium moves right. That means we make more products than we do reactants, okay? Because there is fewer moles of gas on the right-hand side of the equation, okay? I don't think it is, and I'll tell you for why. The Haber process is, I believe, endothermic. And that's because, oh, forward reactions, there you go. Yes, that's right. No, I'm an idiot. Charles Yeah, should make sense when you do A-level stuff and degree stuff. Hetero bonds are better. Higher, bit of mixture, but this in particular stuff is really higher. That is kind of everything. Le Chatelier is higher, really. So let's think about the energy. So if I increase the temperature, yeah, I should have thought about this. Right, so if I increase the temperature, Le Chatelier's principle, the idea that chemicals are annoying brothers or sisters, they say, I want to minimize the increase and try and decrease. So if that's exothermic, that would raise that would exit heat, that would raise temperature. This way is endothermic, that would absorb that heat. So what that means is the equilibrium moves at left in this case because it will absorb that excess heat, because the reverse reaction is endo. Okay. Right. So where does that manifest itself? Where does that manifest itself? The actual conditions for the Haber process, and this is again something which is just in the specification you need to know, is 200 atmospheres and an iron catalyst and 450 degrees C. I will check that they haven't changed between what I used to do. Lovely stuff. It's almost like I do know science sometimes. Okay, so the question, this is like real higher stuff, 6 marker. So if you're like, don't worry about it if it's like really confusing to you. It might go like, why do we select these? Why do I bother? Right? So the 6 marker of why these conditions is really a trade-off between equilibrium and rate. Okay. World Cup ain't on yet, is it? Joke's on you. Starts at 9. The conditions needed is in the separate GCSE. So the Haber process and the use of NPK fertilizers is triple only. Okay. So if I'm talking about pressure, so a catalyst is just good all round, right? Catalyst will make the forward reaction and the backward reaction both go faster, and it doesn't actually affect the equilibrium. So a catalyst is just good all round. Right? Because it makes everything faster. If I now talk about pressure, right? So if I talk about pressure, well, what does rates tell us? Okay, rate tells us that we want a high pressure because of what we said about collision theory. High pressure, about 7:30. So I've been going for about half an hour. So high pressure, because those particles will bump into each other more, fast rate reaction, right? So the rates idea says high, and the equilibrium idea, we've just seen this, says high as well. So we want to do as high a it's all right. I want to do a high pressure. Why would I not do the highest pressure I can? Because if I have a high pressure, I need to have the equipment be able to withstand the pressure. So like 200 atmospheres is a really high pressure. Why would I not go more? Cost more for the equipment. That's it. Right. The temperature. This is the interesting one, he says. Right. This is the one they like to ask about. Right. Because from a temperature perspective, I want a high rate of reaction. I want high temperature from a rates perspective, right? We've said before with collision theory, higher rate of reaction means okay, that higher temperature means we get a higher rate of reaction. You're right there, young man. Someone's discovered the full stop key. Right. So a higher temperature is good from a rates perspective. Okay. But from an equilibrium perspective, we want a low temperature. So why do we use 450 degrees C? It's a compromise. Okay. So 450 degrees here is kind of our like compromise. It's not super high, which would be good from a rate perspective and bad from an equilibrium, right? It'll go really fast, but it really doesn't want to make those products. And it's not super low, which would make loads of products, but really slowly, so there's no point. Okay, so it's a compromise because it needs to balance like the rate and what we call the yield. Okay, hello, is it me you're looking for? I can see it in your eyes. Right, that's Le Chatelier's principle. That was one of the ones on our list. Lovely. Right, someone talked about NPK. Right, NPK fertilizers is just something that, like, again, it's triple only. These are the three things that plants need to grow. Okay, this is generally how quickly we can talk about it. We need nitrogen. Where do we get the nitrogen in a way that can be absorbed? This is where we get ammonia. From the Haber process. So literally that reaction that I just did. P, we need phosphorus. Okay, how do we get that? We can mine it. We can mine it like phosphate rocks. And also, as was mentioned right at the start, okay, yeah, we can do flame tests at some point when we get to analysis. We can take our phosphate, we can take our rock and we can react it with acid, and that will give us our soluble phosphate. Right, and then K, we need potassium. And again, that's something that I believe the spec says you can mine. Yep, you just mine them. Lovely stuff. Okay, easy. Now, I don't think you need to know why, but nitrogen, phosphorus is important for making the backbones of DNA and this kind of energy type of vibe. Nitrogen is really important in making amino acids. Okay. Super triphosphate. Nah, I don't even know about that. Okay. Yeah, I don't really know what you're getting at there. I'll be honest. That's the level of it is. As I said, you can literally. I think it's linked up at the chat. Like if you scroll up, you can do that on the live chat. There's I've linked to the spec. Like that's what it is. Yeah, cool. But like, yeah. Well, where does it say that in there? Like, it says you need to recall the names when phosphate rock is treated with them. I think we tend to kind of focus a little bit, I'd say, on really like one marker stuff. I don't know, why are you in here? You're having a crisis of confidence in one. Right. Organic was next, because I had a lot of people ask about alkanes and alkenes and esters and all of that stuff. I don't know what vibes they are. Vibes of chaos. Right. Organic. It's funny, really, because organic is 1/10 of your it is 1/10 of your GCSE like chemistry bit, and it's basically half of chemistry in real life. And organic chemistry relies on the chemistry of 1 particular chemical. That is the chemistry of carbon. Okay. Carbon is amazing because it can make 4 covalent bonds. And if you've ever done, I don't know, does anyone ever play with Connects? Right, that was that weird like one where you have the bars and they'd like kind of click together. It was like Lego, but you'd use it to make like Ferris wheels and stuff like that for some reason. Roller coasters. If they could only ever make one connection, it would be the boringest thing in the world. Right. Do you go into more depth on using resources? Yes and no. You at A level, yes, there's a little bit more of that. But if you like the organic stuff, that explodes really at A level. It's about like you just can't take everything up a notch. So organic becomes massive because you're learning about more and more functional groups, the reactions which go between them, actually what's going on a chemical level. No, it's not combined only. And stuff like that. In terms of the using resources stuff, you do have a little bit of it, but I would say they deal with more fundamental concepts, really. Right, so carbon makes 4 covalent bonds. Now, the first thing to think about before we go into, I know the first thing technically, according to the spec, is what is crude oil. But let's come back to that. And that is, weirdly, I'm going to talk about naming chemicals. And I'm going to talk about chemical names and what they look like. And this is going to answer when people ask about esters, people ask about alkanes, people ask about alkenes, right? Now, people have a first name and a surname. Now, the surname tells you your family, right? So in Harry Potter, if I think about the Weasleys, they're famously all ginger. That's what they've got in common. Ginger hair and a hand-me-down robe must be a Weasley. Okay, their feature for A level, right? So their surname Weasley means that I can predict that they are. No, we're not doing genus and species. It's chemistry, my man. The surname like Weasley tells you that you're going to know that they're going to be ginger, right? Chemicals are the same thing. We have certain families and they have traits. So we have the alkane family. Love the alkane family. Very simple people. Now their surname, which gives them away as a member of the alkane family, is they end in ane. What have they got in common? Well, they're only carbon and hydrogen. They are hydrocarbons. And they are all single bonds. Okay, our next chemical family that we meet. Okay. The next chemical family we meet are called the alkenes. And their surname, which gives them away as alkenes, is E-N-E. Okay. Now, what makes them alkenes? They are carbon and hydrogen only, same as before. But they have a carbon-carbon double bond. They have to have one. They could have more than one, but really at GCSE level, you only need to talk about one. No, that's A level. You need to know that they do it, I believe, but I don't think you need to know the actual process of it. I think you need to know that they do it. That's it. Nope. You don't even need to be able to name them other than ethylethanoate. Nope, nothing. You're thinking of A level, my man. So, next chemical family. We'll tell you what, we'll come back to we'll do one more chemical family before we come back to it. Okay, the next chemical family, they're the mad lads, they're the party town, they're the alcohols. Now, they are not carbon and hydrogen only now. Their surname is Ol, all right? And what gives them away is that they have an O and an H on them. That's what gives them away. Now, what are the first names? Now, in class the other day, I was talking about this. There's a really posh kind of Tory MP. I don't know if he's an MP anymore, probably lost election, called Jacob Rees-Mogg. Now, Jacob Rees-Mogg he's really posh, but his sixth kid he called Sextus, because that's like the Latin word for six. So he literally called his sixth kid Six, right? Now, weirdly, that's what chemicals do, okay? The first name tells you how many carbons. Okay, it is Elon Musk type stuff, to be fair, right? So if I give them the first name Meth, that means that they've got one carbon. Eth means they've got two. Prop means they've got three. Bute means that they have got four. Everything after that then becomes the shapes that you did at like primary school. So it's then like pent for 5, hex for 6, and so on, right? So let's put this together. Let's say that I had, right, using our naming convention, let's say that I had hexane. No, let's do propane, right? Propane and propane accessories. So the ane part tells us it is part of the alkane family. That means there's carbon and hydrogen only. The prop part gives us our first name. That tells you there's 3 carbons. All right. If you're worried about how to remember them, I always think of monkeys eat purple bananas. Okay, so propane has got 3. So let's do 1, 2, 3. Always draw our carbon chain first. It's an alkane, so everything there is a hydrogen now, and there's all single bonds. We said that carbon has 4 bonds, so that means I need to make sure that every carbon has got 4 lines coming out of it. This one's got 1, this one's got 1, so 2, 3, 4, add on the hydrogens. This one's already got 2, 1, 2, so 3, 4. And then we have propane. Let's do another one. Let's say I have got pentanol. Right? Right. That means 5. Okay. That means alcohol family. That means it has to have an OH at the end. Okay. Now, when you are doing A level, you actually know that you can specify whereabouts the alcohol is. You are not doing A level, you're just doing GCSE. We pretend it's on the end. You don't actually really need to draw this. You just need to be able to recognize it. So 1, 2, 3, 4, 5, alcohol. Then make sure every carbon has 4. Again, for combined, you only need alkanes and alkenes. For triple, you need to know or at least recognize these other ones as well. Okay, so let's look at those alkenes. Okay, let's do another one. Let's do an alkene. Let's do butene. Okay, bute tells us 4. Ene tells us it's an alkene. So because it's an alkene, that means I must have a carbon-carbon double bond. When I draw that, 1, 2, 3, 4. Pick a random one to make it double. Bosh. Okay. Then I've got to make sure every carbon has 4 lines, which I can stick hydrogens on. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That would be butene. Right. Some other triple only kind of chemical families that you need to be aware of. Okay, so these are triple only. Is the carboxylic acids. And these end with that. That's what gives them away. Now be careful because that carbon counts in the number. So if I was looking at propanoic acid, the prop means 3 and the anoic acid means it's a carboxylic acid. So 1, 2, 3, that carbon counts into this. Okay, that is quite tough. It's quite a weird one. What makes it an acid is this hydrogen can snap off. Okay, and then esters. To go talk about esters, again, this is triple only. Okay, someone asked about esters. Well, if I take ethanol, sorry, not ethanol, this is ethanoic acid, this is vinegar. Okay, and I take ethanol, I'll draw it backwards. Okay, what happens is, okay, you see here, I've got an OH and an OH here. They're like, hang on, what are we doing there? Equilibrium's already been done. Feel free to scroll back, talk about that quite a lot. What happens is they go, hang on, we've got a whole water here, let's get rid of that water, and let's snap them together. Let's move that up. Okay, what makes this an ester is this whole linkage here. It's like a carboxylic acid, but this then continues on to more carbons. That is what makes it an ester. You do not need to know, explicitly says in the scheme, that you do not need to know how to name them all. The only one you need to know is this one. This one is ethyl phanoate. Okay. Esters are quite smelly. They're quite nice. I think this one smells of pear drops. I have made it before. The other thing to remember about these is, imagine I had something with two of these on the end. They could stitch all together and you can make a polymer. So because you are releasing water or a small molecule, you are releasing water, and that it's polymerization. The person who's asking about esters, hopefully that ticks your box. But going back to organic. Okay, what is a good source of all of these chemicals? The good source is crude oil. But in its current state, it's useless. Okay, because it is a mixture of many hydrocarbons. And I can't use them all, right? If I've got them all mixed together, that's not useful. So what we need to do is we need to separate them. And the way that we separate them is we do fractional distillation. Again, feel free to put any questions in there if I've missed anything for you. So what happens is we take all our crude oil, and we put it through a heater. And what that does, it will turn it all into gas. No worries, good luck. So this is now going to go in there as gas. Right? And what I have here is this very snazzy thing. Now, if you've watched the news and you've seen like Ukraine have been doing drone strikes on like Russian refineries, and they have these big like towers and they're like burning and stuff. They're hitting these part as well as the storage, right? So I'd say rate is learnable, mate. As I said at the very start, I went through collision theory. If you can get that nailed down, that's like a 4 or 5 mark written question, like nailed in. Right, so it all goes in as a gas. Now, the first thing to remember so if it says explain the process of fractional distillation, you take the oil, you heat it up until it all turns into a gas, right? You then stick it into this thing. This is called a fractionating column. And crucially, it's hot at the bottom, like I am, and it's cooler at the top. So we have this kind of gradient. And what happens is they go in as gas, and basically they will condense at their boiling point. Right? So let's say I'm a chemical which really doesn't want to be a gas. I've got a very high boiling point. I go in here and I'm like, nah, not fancying it. I'm going to become a liquid straight away and drip out the bottom. If I'm someone which is quite happy being a gas because I've got a low boiling point, goes in. I will check. I don't think you do. I would say the trend, at the very least, the trend is the most important thing. Knowing that the shorter ones are at the top and that the longer ones are at the bottom. Okay. You need to know, you need to recognize the chemicals from it. So you need to know that there is petrol, there is diesel, there is fuel oil, there is kerosene. These are all products from it. They are explicitly mentioned in there. You do not need to know them all exhaustively. It is not like the electromagnetic spectrum. It's not like the electromagnetic spectrum where you need to know it in order, back to front, everything like that. As always in science, often the trend is more important, right? The overall kind of vibe that the process is giving you is often more important than the actual specifics. That's why I don't like people memorizing the periodic table, because the periodic table is all about trends. So what is the trend? What are the trends here, right? The trends here is at the top. You know when we were doing all of our naming our chemicals? Right? It's basically like this, right? At the top, you have the real short ones, the real short chains. And down here, you have the long chains. Okay. Right. So how does that translate into properties? Okay. Short chains have a low boiling point. And long chains have a high boiling point. Okay, so if the way I like to explain this is, imagine I get a strip of paper. Right, there's two long strips of paper. Imagine I got some glue and I stuck them there and I put that down. Right, and then I've got two short bits of paper, bit of glue, like that. Which one is going to be better stuck together? The long one, right? Because I've got all of that glue between them. They're longer chains, okay? They stick together nicer. So they have, the long chains have a high boiling point. Why is that? Because you've got lots of intermolecular forces, okay? Whereas the short chains, they haven't got much, they haven't got much glue between them. Okay, so that's not many. Right. What does that mean for the other stuff? Short chains. Oh, here you go. No, there's a pen on the floor. He's nailed it. He's actually nailed that. It's beautiful. Right. These short chains, they've got a low boiling point. They're also they've got a low viscosity. That means that they are runny. Right? Petrol just looks like water, doesn't it? Whereas tar down the bottom it looks like honey. It's like gloopy and thick. Okay, so this has a high viscosity. That means it's thick. We'll do it with 2 C's. Why not? Live life on the edge. Okay. Here, right, they have a high volatility. And what volatility means is it's its ability to turn into a gas. The typical chemical I can think of with high volatility is nail varnish remover. Okay, you're vaguely near nail varnish remover, and you know that you can smell it, right? Whereas you don't walk past a road and go, oh yeah, that smells like road. Okay, so that has a low volatility. And then the other thing is these are highly flammable. Okay, they set on fire really easily and they burn clean. Whereas down here, they have a low flammability. And again, the typical ones that I would say to help remember those trends is I think of we get petrol at the top and we get bitumen or tar at the bottom, right? Is like they are the extremes. Petrol is really flowing. You can smell petrol from a mile off, right? It sets on fire really easily. That's what petrol's like. The tar which goes on our roads is thick, it's gloopy. You don't really smell it. How long left, Karis? I was probably going to do another 15 or so minutes. I mean, I'm not forcing you. Yeah, so that's those. What does that lead to? Oh yeah, cracking. Right. So when you do, because we said crude oil is a mix, right? Crude oil is a mix. Okay. Right. It won't, but it could, right? So what do I mean by that? Is there's this rule which says that, again, I said this earlier to you, just get into the habit of little bits after school. Make sure that you build healthy habits in terms of your work and yourself. Exercise, get out. Make sure you do your hobby, otherwise you get fried. If you start going at full like year 11 whack at the start of year 10, you'll be fried before the exam. Yeah, I'll do an event. That's a good idea. I'll do that. That's a good play. That's a good thing to do. But I'll just talk about cracking first, and then we'll do the life cycle assessments. Love that energy. That's a good idea. Right. When you do your crude oil, right, you get a mix, right? So you'll get your petrol, you'll get your diesel, okay, you'll get your fuel oil. I would love some fuel oil. I'm on fuel oil at the moment, okay. I literally have a tank out in the front of my house, and the price has quadrupled since the Iran war. I can't get hold of it. So if that runs out, I'll have no hot water. Yeah, absolutely, Jaden. That's the one. You've then got things, yeah, it's a longer like that, right? Now, when you do this people want, right? You go to they literally have things on each road where you can buy petrol. So this has got a high demand. Okay, and stuff up here has got a low demand. We don't care about that as much. So what that means is, because that's on a high demand, we kind of have a lower supply of it than what we want. It's basically economics if you do A level. Okay, and over here we've got a higher supply than what we need. I was talking to someone earlier today, actually, and I compared it to opening a pack of fruit pastels, right? Some people are fussy and they only like the red sweets, right? But you have to, when you buy fruit pastels, I know they do it. I know that's a bad example because they do sell just like the purple and red ones now. But if you bought a pack of fruit pastels, you get all the colours, right? But really, the thing which you really care about is your favourite one, which might be the reds or whatever. Now, if I came to you and I said, I tell you what, I know you've got to buy all of the fruit pastels, but I've got a secret technique which will turn those like yellow ones that you don't like into the red ones that you do like. You'd be like, yes, sign me up, love that. Okay. So what cracking does is it says, right, I've got a lot of these and I can't really sell them, but everyone wants these and I ain't got enough of them. So cracking says, right, let's turn that into that. And what we do is we take a long alkane and we turn it into a shorter alkane. And it also has the added benefit of giving us an alkene. By the way, I didn't talk about it earlier, but one of the tests for an alkene, it's the alkene test, is if I take it, right, and I add bromine water. There you go, loving it. When I add that, it will go colourless. Okay, so it would go like that. Okay, wouldn't go cloudy, so it goes colour. So bromine water is orange. The cloudy one is lime water. That's your test for carbon dioxide. So, you know, like here, this might be our fuel oil, and now I've made petrol and the alkene. right? This, I can sell, lovely stuff. All the money. This I can use to make things like plastic, or technically we call that polymer, don't we? Okay, lovely stuff. So it's like a win-win. How do you do this? You have to use a high temperature, and we use a catalyst. Okay, you can use steam. Weirdly, there's also you can do it with an iron nickel catalyst. Right, 6 marker. I love that idea. Let's do it. Pow! Right, let's see how long it takes me to find one on the paper, because I bet it will take like seconds, because they love it. He loves it. Oh, look, I literally opened it. First page. Boom. Right. This question is about the materials used to make bicycles. Here is a bicycle. I love that. As if, like, if you're rocking up to the exam and you don't know what a bicycle is, I think you've got bigger problems. Right? Frame, chain. Never seen one before. Okay. I like. I think I've had the peak concurrent viewership on me weirdly looking at a bicycle. Right. Will we always get a table and a picture with it? No, not always. But if it's wanting you to do a comparison, I can't think the picture. No, but I can't think of one recently where there's not been a table. At least, like, they have to give you information. You do not need to know necessarily their order. You can't see the question because the question's up here. We'll come to that. Don't you worry. I mean, you don't. You can even predict the question, Jaden, because it's going to be like what one's better, isn't it? Okay. So the question does say, evaluate the use of aluminium alloy and bamboo for making bicycle frames. So the first thing to remember is this is an evaluate question. Evaluate questions mean you need to kind of look at both sides. So I would say you say we're going to be doing why aluminium is good. Okay. Well, what we're doing is a life cycle assessment. I think people think that life cycle assessment is something that is like a very delicate process. When you look at this table, right, it considers it at every point in its life. So you are looking at it from the perspective of a life cycle assessment. Yes, it talks about life cycle assessments in a more formal way in other places, in other long questions. So I'll find another one of them, okay, in a second. But like what you are essentially doing is a life cycle assessment. So if I'm evaluating, I'm going to look at why one is good. So let's say why aluminium is good. I'm then going to look at why bamboo is good. And then crucially, you need to give a conclusion, what one you think is best. Now, here's how I like to do the tables. Yes, you do. Now, it doesn't need to be long. You're not after some kind of big thing. But part of the mark scheme is that it's done by tier. And if you don't give some form of judgment, you can't access the higher tier, a level 3 response. What it classes as a judgment, I've noticed, has got laxer and laxer. So as long as you say, like, this is better, sometimes they count that as a judgment. I would say avoid any complication and say, overall, I think at the end, like you're doing is it a 5 marker in RS? You know, where you say some people believe, other people believe. Yeah, probably around 9. So I like to use the table, okay? And what I'm going to do through is I'm going to go through and I'm going to see which one wins, like top trumps, okay? Now, when the biggest mistake I see people make on these long answers is people then just regurgitate the table in there. We need to think, why is it better? So the raw material here is aluminium ore, and the raw material here is bamboo plant. Which one is better? I think we're going to go bamboo plant with that one. Now, if I just said it's made from bamboo plant, that tells us nothing. Why is bamboo plant better? Because it is renewable, isn't it? We're doing a life cycle assessment to answer your question, Jaden, right? We're saying, why is that raw material better? It's renewable. It's not going to run out. Okay. Aluminium ore. Okay. You have the damage of mining. Okay. It's going to, you have to do electrolysis to extract it. Okay. So you have the the CO2 kind of from the electrolysis, all sorts of things, right? Bamboo plant, renewable. If I want more, I'll grow more. Easy. Right. The cost. I think we can say that we like, I know I'm not money bags. That's going to be better. The strength. Okay. This one is a higher strength. So, but again, if I'm thinking, I've got to have in my head, why is it better every time? Because I think it's obvious that you'd want a higher strength, but why? Right? So why is that better? Because it's less likely to break, and therefore you don't need to replace it. Right? It's durable, yeah. It's durable means I don't have to replace it. So why is being durable good? It means I don't have to replace it. You could also argue from a safety point of view. The mass, right? Do I want it heavier or lighter? We actually want it lighter. Why? Two things. First of all, you could argue from if I'm cycling on a lighter bike, it's going to be easier to ride, but you have less transport, like fuel use, right? If I'm having to haul a truck of heavy bikes, that is going to cost more money, more fuel than a truck of light bikes. The lifespan in years. This one is clearly better. Lasts longer. Why is that better? If it lasts longer, okay, I need to make less of them. All right? Because, if I think about paper plates, right? Paper plates, I'm chucking them out every time. So I'm having to make, like, if I had a paper plate for every meal, I'd have to make hundreds and hundreds of plates. Whereas if I just make one ceramic plate, even though that might take more energy, might faff, it means I don't have to make as many. So even if it took 1,000 times the materials, if it lasts 1,000 times longer, it's better, right? One method of disposal at the end of life: burn to produce heat energy. So that's good, I suppose. Okay, and recycle to make new products. So this, I would say, is almost a bit of a draw, isn't it? It depends on what you want from that. Maybe you'd say here the burning is going to release CO2, right? But then you could argue that CO2 was absorbed when you grew the bamboo plant in the first place. So let's use that table. Yeah, that's exactly what I'm going to do now. You say, look at this, look. I've been here before. So let's do our paragraph why aluminium is best, right? Aluminium is better because, okay, you could do it as a bullet point. All right. Okay. It is stronger. So less likely to break in a crash. Okay. It has a lower mass, so costs less to transport. Okay. It is cheaper to produce, as you've said. Okay. And can be recycled into new bikes, new products. Now, why is that good? So you use fewer new resources. Right. Let's now do the same for bamboo. Why is bamboo better? Bamboo is better because, right? So bamboo is renewable and doesn't, so we can mention the negative of that to help us out. Doesn't have the environmental impact of mining. Okay, it has a longer lifespan. Why is that good? So you need to make less to replace it. It can be burned for energy. Okay, why is that good? Rather than in landfill, right? That's not good, is it? Landfill. Now we need to do our conclusion. Again, doesn't need to be long. Overall, I think I'm going to go with aluminium because aluminium is better because of its strength and cost. I don't know. Doesn't matter. As long as you say overall what you think, I don't matter. Right? I think the thing is the 6 markers on these really do tend to follow this format. Right? And it is like that skill we can practice. Hopefully you follow through there, right? That I can kind of see which one wins. What a question on one? Yeah, I can find one. Like we can see which one wins. Okay, and then do that. Why do they not be protection for corrosion? Yeah, sure. So aluminium has a protective layer of aluminium oxide, preventing contact with oxygen. It's basically protected by its own rust. This is a triple paper. It's not because it's unreactive, weirdly. So aluminium is actually really reactive. It's that the outside of it. No, don't go. Ooh, that's fine. Like it's quite a weird thing because like aluminium is really reactive, and it's so reactive the outside has already reacted. But unlike rust, right? When I have like iron oxide, right? So I have iron, it rusts. The iron flakes off, so you have more iron to now attack, and it will slowly eat it away. Aluminium oxide will just kind of stay on there, and it kind of then prevents more getting through to it. It kind of makes its own lid, if that makes sense, right? So it has a protective layer of aluminium oxide preventing further contact with oxygen. That's basically it. It's like it's protected itself by, it's basically protected itself by already having rusted a little bit. It's like, obviously with iron, we paint it, so we have a protection from the oxygen. All right, so painting or oiling it will prevent that contact with oxygen, which does the corrosion. Aluminium has basically made its own paint, for want of a better term. Don't write that. The aluminium oxide is a protective layer. You wanted a what was it? A reversible reaction one. Let me see if I can find one. Has anyone got any other questions, by the way? We didn't talk about sewage, did we? Shall I quickly do a sewage on the way past? Let's do that. Okay. Water collected from rivers is used in homes for drinking and flushing toilets. Water used in a home must be potable. That means that it is drinkable. Sacrificial protection. So sacrificial protection is where so let's say I've got a boat, right? And boats are made of steel, mainly because it's cheap and strong. Now, the thing is if that steel rusted, the iron rusted, I now got a hole in my boat, and I think we can generally agree that a hole in a boat is bad. For example, Titanic. So I don't want that to rust. So the first thing we do is we paint it. But the other thing we do is we say, right, what we'll do is we'll bolt a lump of zinc to it. We'll literally bolt a lump of zinc to it. And the thing is because zinc is more reactive than the steel, because of electrochemistry, the zinc will kind of corrode first. And that stops the corrosion of the steel. So what you can do is you can keep adding lumps of zinc or something like that onto it, and then that means that your boat itself won't rust, and that zinc will rust instead. So that's why it's sacrificial protection, because that's kind of taking one for the team, sacrificing itself and being corroded. Okay, so process A, to produce potable water. Process B is to treat sewage. Okay, it says, so potable water is safe to drink. Wastewater produced after use in the home is called sewage. Figure 3 shows how water is collected from rivers and returned to rivers after use. Explain what happens in process A and process B. Do not refer to the use of water in the home. Okay. So, broadly, if I want to make something drinkable, I want to make sure that it has got nothing in it which will hurt me, and there is nothing in it which is just not nice. Okay, so what I want to do is I want to remove the bits and the solid. This is technically triple, but the idea of producing potable water and stuff is combined. That appears fully on the combined paper. Okay. Okay. So, how do we get that? So the water here coming from the river, right? It's going to have bits in it. So what we do is we filter it, basically. And that can take the form of, you have a screen. So imagine I'm following this arrow. We have a screen which takes out the big bits. Then we go through filter beds, which will remove the little bits. Okay. And then I want to now kill the microbes. So we now do sterilization. And that sterilization will remove the microbes. So the filter bits and the screen, they make sure it's just the liquid. Okay. And then the sterilization, that kills the microbes. So now that's all gone. All right, so now that should be safe to drink. When I look at process B, okay, again, you've got a screen here. You get rid of the bits. Then you have the effluent. Then you leave it to settle. You can do aerobic and anaerobic digestion. Now notice there is not any sterilization because we're not worried about making it drinkable. We're just making it safe enough to go in the river. Okay, so you're removing the bits, you're treating it to the point where it's kind of is not dangerous, it hasn't got poo in it, right? But you're not making sure it's drinkable. Okay, so that kind of follows it through there. So when it says process A, what you're doing with process A is you will filter it to remove the solid. Yeah, I explained sacrificial protection, Dempsey, but thank you for a lovely explanation. Then you do sterilization to kill the microbes. Right, and you can do that with chlorine or UV or ozone. Right, now the reason we don't have to talk about desalination is because it's come from a river. Okay, so it's come from fresh water. You can see here that it's come from fresh water. If it wasn't, it was salty water, you'd have to do desalination to remove the salt. So what's going on in process A? Or process B, sorry. You have screening to remove large lumps. You then have settlement, like settlement tanks. And they allow the small lumps to sink to the bottom. Okay, then we do check exactly what they want precisely from it. Yeah, no, I'm right. Cool. So we now do aerobic treatment of the effluent and anaerobic treatment of the sludge. And then that can go into the river. So it's now safe. It's not drinkable, but it's safe. Right, someone wanted a question on the reversible. Oh, there you go. Look, water molecules. What sentence describes this reaction at equilibrium? So remember, equilibrium is going forwards and backs at the same rate. Okay. Cool. Right. Does anyone have any final questions? I'll kind of bring it a bit to a close. I've got to about 9 o'clock. I'll be honest, I'm feeling a bit tired. I've been rambling all day. Did loads of year 11 stuff. You lot are probably all bored of me anyway. Do you have any particular questions that I can answer before I go? And also, obviously, I don't want my wife to think that I'm a complete sabo. I mean, she knows, she thinks that anyway. Cool. If there's no particular questions, okay, I'll leave it there. I've gone through quite a lot of random stuff in there. Hopefully you find it useful. The big area I suppose I didn't really cover is like the tests. Yeah. For separate, yeah, there's a lot of tests. Genuinely, like, it's hard for me to kind of like. It's just a lot of rote learning, by which I mean like just information you need to get into your head. Now, I'll link to the spec. All right. So if you look at that in the spec, right, you can see. So the full gas test is the same for combined, right? You need to know lime water for carbon dioxide. Oxygen is relighting a glowing splint. Hydrogen is the lit splint and it does the squeaky pop. Chlorine is you take your chlorine gas and you put damp litmus paper and it bleaches it. Then it's for the positive ions, that's the flame tests. And then you also need to do the metal kind of hydroxide tests. Okay, so what you do is you take the aluminium, calcium, or magnesium ions, and then when you react them with sodium hydroxide solution, they make a white precipitate. If you keep adding it, the aluminium hydroxide will dissolve. Carbonates will bubble. Halides make like white precipitate, cream precipitate, or yellow precipitate, depending on where they are in the halogens. And then the sulfate test is that you produce a white precipitate with barium chloride. I know that's a lot of a ramble, but genuinely, like, it's just sections of like, here's the test for sulfate ion. Sulfate ions in solution produce a white precipitate and stuff like that. That is, well, at least you've got one. What is your mnemonic? Oh yeah, I mean, obviously. I know, but my wife is also a science teacher, so we don't get out much. So, like, you know. Thermosetting means once you've made them, they're kind of locked in. They have lots of like cross links. So what would I use thermosetting? Will be a plastic kettle, all right? Because once I've made the plastic, I don't want it to deform or melt. Thermosoftening means, as the name suggests, as it gets hot, it gets soft. So milk bottles are thermosoftening because I don't expect them to get hot. And if you've ever like, I don't know, I used a milk carton the other day in an emergency to get rid of some hot oil, like, because you're not meant to pour that down the sink, are you? And I put it in there and it made the like thing all shrivel up. It went kind of like that. Contact points. In what way? Don't really know what you're getting at with them, I'll be honest with you. Oh yeah, so when you talk about increasing the melting point, so You remember how earlier when I was talking about organic, Chloe's chlorine, she's white precipitate, and Bradley is bromine, creamy, and yellow, not right. But yeah, that's cool. I always think about it as the further you go. I've done Le Chatelier. I'm definitely not going to do it as I'm about to finish. Le Chatelier earlier in the stream, talk all about it. Talk about like a annoying brother or sister. Right. So remember how earlier when we talked about organic and we said about the long molecules having lots of intermolecular forces, right? If I want to increase the melting point, I can make sure that basically instead of the polymers being branched, right? Imagine they're branched. That means they're like folded and walk like that. If they're like this, right, and they're branched, it's not going to like they can't the glue is not going to stick as well because they're like all bumpy. So if I make sure that they're non-branched, I increase those contact points. I can make it even better by having some sulfur crosslinks. That's usually quite a good one. So if I so for instance rubber, if I add sulfur to it and I heat it up, basically instead of it being intermolecular forces, it's like literally joined together now. See you later. Yeah, I just remember. So I know I think I was saying before I kind of got distracted again. I just remember that as you go down the halogens, they get kind of more off, right? So you know, like your chlorine is white, and then you're getting muckier and muckier. Yeah, it's all to do with branching. So, if I have when I make the polyethene, right, I can make basically a big long chain. You can also have it where it starts to make branches like that, right, or it kinks off. Now, if I have them all in a nice thing here about branches like this, can you see how they'd all stack together nicely? And because they'd all stack together nicely, this is high density polyethene because they all kind of will go together. Whereas here, those branches mean that I can't like kind of get them together. Yeah. You know what? I'm hopeful for tomorrow. Yeah, chromatography is nice. Like when you're talking about the results of chromatography, I think that's quite solid. Okay, right. I am going to go. The like replay, like the comments on that. I won't monitor the live chat because I think it dies when I kill the live stream. But if you are looking at the VOD and comment on it, I'll probably reply before the exam. I hope that was in any way helpful, and my absolute pleasure. Have a lovely rest of your day and good luck.